All right, we're going to go ahead and get started. This is Anthony Eggert. I'm the director of the UC Davis Policy Institute. I want to welcome you to today's webinar. This is a collaboration between the UC Davis Policy Institute and the NextSTEPS program, Sustainable Transportation and Energy Pathways program, which is part of the Institute of Transportation Studies here at UC Davis. We've got a great webinar and a lot of material to cover. We also want to make sure that we get a chance to get to your questions. So we're going to have about 30 minutes of presentation, and then we're going to have the opportunity to ask questions. If you are interested in asking a question, you can actually use the chat box, which is in the lower left hand of your screen if you're logged into the ReadyTalk webinar system. Go ahead and type in a question. If you have a question on a particular slide, go ahead and indicate that. We can take questions during the presentation and afterwards. We will not be taking verbal questions just to be able to manage this given the number of participants. And we're not going to attribute the question. So all questions are welcome. This is being recorded, and this will be available. It will be posted on our website subsequent to the conclusion of the webinar. So with that, I'm going to go ahead and introduce our first presenter. And he is Lew Fulton, who is the co-director of the NextSTEPS program here at UC Davis. Lew?
Thank you, Anthony, and good morning, everyone. I will kick off our presentation, but all four of us who you see on the screen there who've been involved in producing this white paper and the presentation will take a turn this morning. So we'll all try to stay brief and get our main points out. So I worked with Nathan Parker, who's a postdoc here, Julie Witcover, who's actually a project scientist. That's a mistake on that slide that I just discovered, and Geoff Morrison, who's a postdoc here. And it's been great to work with this team, and many others here in the NextSTEPS program and around ITS Davis have already reviewed this and provided valuable input. So we're talking about three paths forward for biofuels, and of course biofuels is a very big topic. I've been thinking lately of it as kind of an elephant, maybe possibly even an elephant that thrashes around quite a bit out there, but in any case, we're only looking at part of the elephant like often happens, and the particular deep dive that we're taking is to look at where we stand on both what you might call leapfrog technologies, advanced biofuel pathways and feedstocks, and also at the same time look at more incremental type processes that we're seeing happen at existing biorefineries such as corn ethanol plants, and just try to connect a few dots about what we see out there and the connection to current policies and see what we can derive in terms of some lessons learned and possible directions moving forward. So the outline is shown here. Very briefly, I'll mention some of the backstory on why we should care about biofuels, why we think they're going to be a very important part of our long-term energy mix. And then we'll get into more of the direct topic, what we're seeing in terms of projections of biofuels use out to 2030, what that means in terms of leapfrog investments, incremental improvements, and transitional technologies, and those are sort of the core concepts that we're going to cover. I'll come back to those in just a minute. And the three routes forward that we see for those three types of biofuels, and then the implications for the policy landscape and some final thoughts. So we're going to explain this a little better as we go, but we thought it would be useful to put these key takeaways right up front, and so you have an idea of what we're focused on in this presentation. And the three kinds of biofuels that we are identifying, we're not the first people to think of it this way, although maybe this terminology could be considered somewhat new. The incremental kinds of improvements, it's not so much biofuels, but it's processes and technologies that fall into these categories, different ways to make biofuels across a range of types of biofuels. And the incremental approaches are small improvements in existing biorefineries. This could be such things as corn ethanol or soy, fatty acid methyl ester, biodiesel production facilities. And we are finding that these kinds of facilities are making investments that can rapidly achieve near-term reductions in CO2 emissions, at least in terms of direct CO2 emissions and in terms of rated CO2 emissions. We'll come back to that. The Leapfrog are these longer-term advanced technology and advanced feedstock types of biofuels that hopefully will be quite sustainable, low net greenhouse gas emissions, although there's a whole lot of issues around even defining what net greenhouse gas emissions means. Typically cellulosic feedstocks. There could be some advanced technologies to convert those cellulosic feedstocks into either ethanol or various drop-in fuels. The feedstocks could be crops, but they could also be waste materials. So there's a big range of types of feedstocks and technologies there that we want to look at. And I'd say that the issue right now is that we are not seeing large-scale investments in those kinds of pathways and routes. I guess I should say routes because that's the term where the three different routes that we're looking at. And we want to understand a little better why we haven't seen that much progress yet on Leapfrog and maybe why we won't for the near term. And then there's a kind of transitional set of technologies and routes, this transitional route that often shows up as bolt-on, meaning that small investments, small additional production equipment at existing biorefineries, but that get into the use of advanced technologies. And so these are kind of a linkage between Incremental and Leapfrog. And we are seeing a lot of activity there at existing biorefineries. There's increasing use of cellulosic parts of, for example, corn plants. And we think it's an interesting trend that we want to try to understand better. So that's the basic set of takeaways, and now we'll go into this in a little more detail. I will back up to cover the fact that a lot of international models and national models, for that matter, show that if we want to achieve a low carbon, a low greenhouse gas future in transport, it is going to be very challenging to do this if we don't include a substantial quantity of biofuels in the mix. There are possible ways to do it without biofuels. Mark DeLucchi has been involved, our colleague Mark DeLucchi has been involved in studies that show ways to do it completely with wind, water, and solar power and using electricity and hydrogen as your energy carriers. But there are a lot of challenges to doing that without biofuels, especially for your heavier modes. And in this IEA projection, by 2075, you have about 50 exajoules of advanced biofuels as part of your low carbon, near zero carbon transport energy system. So it's certainly being counted on to play a key role in the future. And then that same IEA projection shows, when you break it out by mode, that although it may be possible to decarbonize light-duty vehicles, PLDV, passenger light-duty vehicles there on the left, with mainly electricity and hydrogen, other modes such as air and waterborne shipping are expected to really be relying very heavily on biofuels for the foreseeable future. So that's a little bit of a backstory. And now I would like to turn it over to Nathan to get back to our main topic today.
Okay, so what we're looking at today, another reminder about what we're looking at. As Lew said, the biofuels are an elephant, and we're looking at possibly a wiggling shin bone of the elephant here. And we're looking at the growth in biofuels, and apparently faces many constraints. There's demand side, the ethanol blend wall, some supply side issues, and there are many unresolved issues on full environmental impact of these fuels and what's the appropriate policies to get them up to scale sustainably. But currently, what we're focusing on here is a near-term supply-side picture for the U.S. So once again, focusing on spatially in one area. And for the greenhouse gas emission profiles, we're looking at more on what's currently as assessed in policies, not a comprehensive assessment of climate effects from the policy. So what's going on with biofuels, the expectations for biofuels from both the public and experts has been on a roller coaster ride from 2005. Here we're showing the Department of Energy's projections from the Annual Energy Outlook from 2005 to 2014 for 3 snapshot years, 2013, 2020, and 2030. You can see that for the years after the passage of the Renewable Fuel Standard, which happened in December 2007, there was an explosion in expectation of non-corn biofuels, non-corn ethanol biofuels, in 2020 and out to 2030. But in the recent years, in 2013 and 2014, those expectations have dampened, and now they're not really expecting much out of these fuels anymore. And significantly, here we have, so in the black is corn ethanol, and the red are cellulosic ethanols. And you can see in 2030, the mid-year projections had a lot of expectation of cellulosic ethanol, but due to the blend wall issues, they are now expecting very little contribution from cellulosic ethanol. And then, so cellulosic ethanol and the yellow here, the other biofuel, are kind of what we're considering the Leapfrog technologies for biofuels. And there was a large expectation long-term for 2030 to have a lot of other biofuels in the mid-years, 2008 to 2012, AEOs, annual energy uplifts. And now that those have been dampened a lot. So what we're trying to do with this presentation is explain some of what's going on here. So there's a real diversity of biofuels, and so it gets kind of difficult to talk about because there's just a lot of different kinds and types. And so what we want to focus on here is that we're kind of trying to look at biofuels on 2 dimensions. One is the financial risk, or the commercial, how easy it is to get these fuels into the market commercially. That's on this figure, it's the x-axis. And then the other is the reduction in carbon intensity from these fuels. So the Leapfrog technologies that we're talking about, that we're kind of from the renewable fuel standard, what we were thinking were going to come into play to fill that role. They're low greenhouse gas emissions, so a large reduction in carbon intensity, but because of the technologies, the scale of these technologies, they have to be large facilities in order to be profitable. So that means they have a very high capital requirement, and a high capital requirement on an unproven technology is very risky. So they tend to be this technology that it's hard to come up with a good business model for them coming into play. And while this has been slow in development, and we've been watching it, and expectations are waning on the Leapfrog approach, there's been some interesting things happening down on the other end of the scale, where there's small investments that lead to small improvements in carbon reductions, but these are happening on existing facilities, and so there's a lot of scale there. There's 13 billion gallons of ethanol out there, and if you can make a small reduction on each of those gallons, you can make a pretty big cumulative impact. So this is what we're talking about in terms of incremental. These things have very short payback periods, things that people may be doing solely for economic reasons, so they save energy and save money. And the third is looking at routes to get between the incremental and the Leapfrog. There seem to be some technologies that are being deployed that are more heading up the greenhouse gas, good greenhouse gases, getting into cellulosics, but with kind of more of putting a toe in the water instead of dumping your doing cannonball into the lake. And the fourth little category that we feel like we should mention, but we don't actually cover very much in this, is kind of waste-based fuels. so like waste-based biodiesels that have really good carbon intensities and relatively low financial risk. But the problem with those in terms of thinking about long-term, they have a very limited scale that they can go to due to the resource base that they pull from. Whoops. I wanted to go through that very quickly, but not quite that fast. So this is a table that kind of covers basically what I just said while going over that figure. So it's in the slide deck for your information. So now I'm going to show there's some examples of the Leapfrog firms that what has been established. There have been several plants built. But they've had trouble getting going and producing fuels at the rates expected. There's a facility producing cellulosic hydrocarbons that Keor built in Mississippi, and they tried to operate it for a year, and they had trouble getting the feedstock flow rates and the yields that they were expecting from their demonstration plant. The scale-up was not working very well. And kind of similarly, the first cellulosic ethanol standalone facility in Italy has been very slow to start up. They announced production, that they could produce cellulosic ethanol, and then they haven't really been producing very much since then. And then there's a few other technologies or companies out there who are building these plants, and it's kind of these are greenfield, often with startup companies who don't have very much experience in this particular field. And so it's an interesting area where there's a lot of things can go wrong. And
a lot of learning needed.
And a lot of learning needed. So operating this, I'll turn off my pointer. So there's been, in the last 5 years, $8 billion have been spent by the federal government, venture capital, and energy companies in an attempt to get this Leapfrog technologies off the ground. So what have we gotten for this? We haven't gotten very much fuel at this point, but we've gotten a good bit of market movement. We've had a lot of entries, a lot of companies, firms being started and expected to produce fuels in the future, and a lot of learning on what you can do with these technologies. So this figure is here. Most kind of probably best to focus on the right-hand side, but cumulative. So this shows the number of firms in the U.S. In the biofuels, in this kind of Leapfrog biofuel space, who have announced that they will be trying to build a facility to produce these fuels. And we have it broken down by different types of technologies, of biochemicals, so kind of cellulosic ethanol, pyrolysis with hydrotreating, gasification. These are two thermochemical processes, and algae transesterification and other. You can see that there's pretty significant growth between 2000 and 2010, a big boom between 2005 and 2010. And this is a database. This is based on a database from about 1,700 biofuel firms globally. And so we might be missing some of this, but we're within the U.S. And so this current, what we're seeing here right now is that the things are kind of flattening out in terms of new firms coming in, but this may be a bit of a lag in data. That's what we know at the moment. And then I'm going to turn this presentation over to Geoff, who's going to talk about the incremental technologies.
Okay, so like we've mentioned a couple times, there's also these developments that are happening at existing biorefineries. We're calling them incremental improvements, and these are just a couple examples up here on this slide. But we've done a big lit review. We've talked with engineering firms that do engineering for biorefineries, and we've looked through the low carbon fuel standard documentation. All of these sources are really great. In particular, the low carbon fuel standard documentation has kind of biorefinery level improvements that are happening, and they'll talk about shifting from natural gas to landfill gas, and what carbon intensity improvement they're getting based on that. And so we have a very rich data set right now that enables us to track at the biorefinery level. So again, Incremental are low investment risk, but fairly low carbon intensity reduction. But there's a lot of biofuel to improve upon, so that's a big pool. The next slide, this is just showing a couple of these carbon intensity reductions. There's improved the process fuel, improved the pretreatment or energy efficiency at the plant. Each of these is adding, typically less than 10 grams per megajoule improvement to your plant, and they're not necessarily cumulative. You couldn't necessarily add each of these improvements and get, whatever that is, 50 grams improvement. But each individual one is improving our existing system. And then kind of our last of the three routes that we've been talking about is this transitional. And so these are slightly more investment risk than those incrementals, but improvements, but maybe less than the full Leapfrog. And we are seeing a lot happening in this space. And specifically, there's biorefiners out there that are using the corn stover, corn fiber, and the bagasse material for some of the Brazilian biorefineries. These are all basically just coming online last year and this year, the latest ones. And so this is a very new space, but if you use corn fiber, you can actually boost your yields at your biorefinery by 2 or 3%. If you use the stover, then based on our calculations, kind of on a per hectare basis, if you want to pull off the stover in a sustainable way, then you can get up to maybe about a 30% improvement in yield. Bagasse, it's even more if you're using the bagasse, and so these are pretty big yield improvements. However, because the investment risk is slightly more than just an incremental type of improvement, the ramp-up rate of these is likely to be not as fast. And so this leads to kind of one of the big questions we posed in our white paper, and we invite you to read our white paper. But do these transitional improvements that we see, is that going to be a path to leading to kind of full Leapfrog standalone cellulosic plants? And it definitely is worth noting that right now each of these transitional developments is making ethanol, and so there may be some demand side constraints with the blend wall there. And then the other thing to note is they're using sort of the existing cropping system. So we're not talking about switchgrass bolt-ons right now. We're not talking about poplar bolt-ons as much as we are corn fiber, corn stover, and so one question is this actually entrenching us further in the sort of corn realm? Okay, and then this is slightly a busy slide, so I apologize, but this is what happens when we kind of put all our three routes together and make some projections into the future. So just start with the left-hand side graph. This is biofuel production. So this is gallons, gasoline equivalent. And it's probably easiest just to start with that gray Leapfrog curve. So this is kind of what we think the greatest ramp up of Leapfrog biofuel in gallons per year could be, so about 7 billion gallons by 2030. The blue would be what we think is feasible from the Stover and the fiber ramp up, and then that orange band is it's slightly different than the other two colored bands, but that orange band is what you're getting from incremental improvements. So this is gallons that are being improved at corn and biodiesel plants. So we can take that left-hand side figure and translate it to the right-hand side figure in terms of greenhouse gas reduction potential. And what we see is these incremental improvements that we've been talking about. Even though you're getting a small reduction in carbon intensity, there's such a large pool of existing biorefineries to improve that you're going to get quite a bit more greenhouse gas reduction, at least in the near term. And then, closer to 2030, if you're really aggressive with the Leapfrog, then the Leapfrog might be getting you more greenhouse gas reduction. But certainly in the near term, this incremental improvements are going to get you more greenhouse gas reduction.
Okay, so I'm going to talk a little bit about the policy landscape that sort of provides a backdrop for these developments. And what the key thing here is that there are two major low-carbon fuel policies that provide the backdrop, and they have different policy designs. On the left side, you see a compliance schedule for the California's low-carbon fuel standard, and what that my little pointer.
So, and this is Julie Witcover is talking now.
Okay. So, yeah, that works. But anyway, it shows the compliance schedule for California's low-carbon fuel standard that has annual carbon intensity targets with kind of a goal of reaching 10% reductions in the whole state's transport energy fuel pool by 2020 from 2010 levels. And the key here is that the target is carbon intensity, and the market really decides what's the mix of CIs and there we go, CIs, thanks, Liz, and volumes.
Goes off over here, you can't see it anymore.
Okay, and volumes to reach those targets. Now, at the federal level, the U.S. Renewable Fuel Standard, on the other hand, really focuses on volumes. And here you see a ramp up. It's a system of nested volume mandates going up to 15 billion gallons of corn ethanol in 2015 and another 16 billion gallons by 2022. And this is just showing you the ramp up. So the carbon intensity gets into the picture because each of these mandate levels, mandate targets, has a carbon intensity threshold that has to be met for eligibility. So we've got, we've got CI. So the only thing I want to point out here is this dip here. There are 2 bars for 2014, and this is some of the discussion we've had about cellulosic showing up and the ethanol blend wall has led to a proposed revision of the mandates downward. And so this has added some policy uncertainty to the mix and kind of brought into question how this is dealt with now will have an effect on the way the rest of the program is rolled out. Likewise, for California, there are some ongoing amendments adding some policy uncertainty. Oh, sorry. Yeah, thanks. Having trouble with the controls. So our takeaway is that currently the policy landscape is favoring the incremental side, and especially via the low carbon fuel standard. Because it's a carbon intensity standard, it values every gram per megajoule reduction. So what I'm showing here in the graph is that with each additional incremental gram of megajoule improvement in carbon intensity, you are adding value, okay, to that product. On the other hand, in the renewable fuel standard, you need to meet these carbon intensity reduction thresholds of 20%, 50%, and 60%. So once you are in a carbon reduction bin, the incentive to move on is, it's a harder bar to cross unless you happen to be kind of at the edge of that next threshold. So we think this favors the incremental approach. Now, both these programs use compliance credits, tradable compliance credits, and the credit prices do provide limited support for the transitional route. And in the renewable fuel standard, there's also a cellulosic waiver price that's brought in when cellulosic production has not met its targets. And this provides a bit of a price premium for cellulosic fuels that could also support transitional. On the Leapfrog side, either of these programs could support Leapfrog investment, and in fact are designed to, if you look at those aspirational goals. But in the implementation, these are huge, as Nathan pointed out, these are huge capital gaps that have to be bridged, and you would need to have a credit price that was high enough to actually bridge that gap in order to make that incentive work. And practically speaking, there are economic and political concerns about those credit prices. So this has added to the policy uncertainty. Policy uncertainty translates in the programs into price uncertainty, volatile uncertain prices, and this favors incrementalism because you can't rely on this incentive to reduce your exposure. Okay, so we've been talking a lot about ratings, and I just wanted to point out something about how these programs work and bring in new pathways. So what this graph is, it shows the green bars. The horizontal axis is carbon intensity. So the green bars are showing you, for different feedstock and fuel pathways, a range of available carbon intensities that have very defined production processes. The blue bars, and for corn ethanol, which we're highlighting here, thank you. For corn ethanol, which we're highlighting here, there are 13, that's the first number in the parentheses, ARB, that's Air Resources Board derived pathways. And there are 84 pathways actually in use, okay? And this includes some new and modified pathways. There are 62 of those. And you can see those are sort of stretching the boundaries, changing the range of available pathways. So the key point is that both of these programs have ways for new pathways to enter into the system. As we've mentioned several times, the rating system for these programs don't necessarily capture the full impact of the technology on climate or other factors of interest. Okay, so we started out with key takeaways, and we're going to stop with leaving you with some final thoughts to try to spark some conversation, because we would like feedback on this. The first is we focused really on ethanol pathways, and as Lew mentioned, in the long run, you're looking for diesel substitutes for heavy-duty applications. So there's questions left about how far to go down the ethanol pathway in terms of infrastructure and thinking about ethanol to diesel conversions. Then, in terms of each of our three routes forward, we kind of think about what lessons have we learned so far and how to build on them. That's kind of the key message. So for Leapfrog, are there key lessons from these difficult startups that can be learned and improved on for next steps? And importantly, one of the things that's tripped up the scale for biofuels is that the environmental safeguards, there have been a lot of surprises about that, and it comes up again and again that there are sometimes very specific conditions for sustainable use. How to identify those in a more systematic way to reduce the surprises, and because these go out into the land sector, they could be very difficult to enforce because of the diffuse nature of the agricultural sector. So there's administrative issues on, once you've identified them, how do you enforce them and how do you monitor them? On the transitional side, we've pointed out, sort of observed that the way this is developing on the ground looks like there could be learning that could help with the Leapfrog route. But the question is, are there ways to actually push that, to make that happen more efficiently, or in a direction that would give us the kind of diversity of feedstock and breadth that the people are interested in. On the incremental side, there seem to be systems in place that are pushing development and diffusion, but is there more needed to both hasten that diffusion, because the timing of emissions makes a difference, and I guess deepen what I've thought of as a neglected margin. So, we've thought basically these improvements, efficiency improvements and ways to reduce carbon are emerging on the landscape, and are there ways to push that further than we have so far? And finally, people have thought about, some people have looked at the slow ramp up and been very disappointed. Others are relieved, and the question is, can this be a breathing space for society to sort of thrash out these different pros and cons now with the knowledge base that we have a few years after rollout, and help to shape policies that really fit better defined societal objectives.
And I'll just bring it home to say that's what we had to say today. We are, grateful that you've been listening in, and we look forward to hearing questions, and I guess there have been a few, so I'm going to turn it over to Anthony now to relate those questions.
Thanks, Lew. So again, want to thank the presenters. We've had Lew, Geoff, Nathan, and Julie. We now have about 20 minutes for questions, and really would want to encourage you to submit your questions. If you want, please type them into the chat box, which is in the lower left-hand corner of your screen on ReadyTalk. We will go through those as they come in. I'm gonna kick this off with my own, and I do see we have some coming in here. But economics, of course, is a major factor. Nathan, you'd mentioned the business case as being challenging for some of these. What do we currently know about the business case for Leapfrog, for Transitional, and for Incremental?
So for Leapfrog, it looks like the business case is that these first plants that you're putting in are probably not going to be very profitable, and that it's really a long-term goal. It's a long-term business plan where you are developing a technology that will, in the long term, lead to a profitable large industry for your company. And so you have to have a really long-term planning horizon and be able to absorb those early losses. And so that reduces the set of people who can actually play in the space very well. For the incremental, it's almost some of the things that are currently happening on the ground are, in some cases, purely a good business case in terms of making money even without the carbon concerns. And from what we were hearing in some of our interviews was that they're looking at the incremental investment as a pure financial pure economics without the policies in play, but they're also looking at it with the policies in play to get a feel for what that value is. So it's the policies are giving them a little extra bump, but maybe not. But the technologies may happen, the improvements may happen regardless. And Transitional will be somewhere in between, where some of them are looking kind of like they're marginally good investments without the policy, but with the policy they're good. They're really good investments. And then
Scale.
And then
They're small scale. So
some of them are smaller scale, but some of these Stover plants are up in the same scale as our Leapfrog considerations, and they're more risky. And so the things are going on there. They're interesting.
Yeah, and that's why the transitional space sort of spans that close to Incremental, Transitional, and close to Leapfrog, Transitional.
Great. So there's a question here. I'm going to jump to this one about waste. California, of course, has a lot of different waste materials. It's not necessarily a corn state, so perhaps not so much stover. That was one of the sort of categorizations of routes, which was sort of up in the corner of low risk and high benefit, carbon benefit. At least that's on that X and Y axis. What do you think about how waste fits into this hierarchy, and where do you see it sort of coming into the system?
So there's a hierarchy of waste. There's some waste that are easy to convert to fuels, and there's some waste that are really hard to convert to fuel. So waste oils are what we are putting in on that figure as low carbon, low risk possible fuels. But forest residues, on the other hand, are a lot more difficulty, have a lot higher difficulty. They're these cellulosic technologies that require these large investments and unproven technology. So in relation to the question on California, the small scale waste that is the waste that are kind of low risk are kind of 1% of your California waste base. To access the bigger waste base, you need to get into these Leapfrog technologies, really.
And also, some of the things that have the label waste actually have competing uses, so might be more difficult to use sustainably than has sometimes been assumed.
Great. There's another question here that is trying to understand some of the challenges that are associated with the facilities that are in operation or attempting to start up in both Europe, and I'll just add in, you've mentioned a couple of those in the U.S., like Kior. Do we have enough information to know the extent to which those are technical challenges, economic challenges, some combination of the two?
I can give my understanding, and it's qualified that this is my understanding, and I could very well be wrong. But my understanding is that the significant factor is technical, that they've had technical issues with the technology not operating as it did at the demonstration scale. So at the larger scale, they've run into new problems, and that it hasn't performed at the level of expectation, and they have some expectation that they can fix the problem with more investment, but that remains to be seen.
Gotcha.
At the same time, on the policy side, there's been increasing concern about all land-based bioenergy and debate about how to bring in land use change into the European renewable fuel policy and fuel quality directive.
Gotcha. So just want to remind people, if you're interested, you can download the slides from our website. The link was provided to all of the registrants earlier in the webinar. A question here about potential changes to the policies, both federal and state, to create incentives for leapfrogs. Is there anything being anticipated or anything that we would think might create stronger incentives for the leapfrog?
I mean, on the basic level, it's a question of credit pricing. So to actually provide the incentive, what the policies do, if to the extent they're staying in place with these goals, they do provide a guaranteed market once these things show up. But in terms of actually incentivizing them, outside the direct funding that Nathan showed through the policies themselves, it really is a political and economic debate about what's tenable in terms of credit prices and incentives. And if you send a clear signal, then the private sector can understand what that gap is and see if they want to work on filling it. But right now, there's uncertainty about what the size of that investment signal is.
And I think that's a general challenge with policymaking, is to provide a clear signal that gives confidence to investors. And I mean, it's just a natural dynamic that's hard to overcome. You want a flexible policy so that market signals adjust to the situation, but investors are looking for some confidence, some certainty. So, that's always going to be an issue, but there may be ways to refine existing policy to provide a little clearer sense of what the ranges of credit prices, for example, would be. I also want to mention that we're going to be producing a white paper on innovations in policy, and we'll be getting into that. So in this presentation and in this paper, we're kind of stopping short just a little bit on being very policy prescriptive, but we'll be getting back to that. So we're very interested in hearing people's thoughts about policy fixes, if you will.
There's at least one bill in California that's being proposed looking at very low, kind of almost ZEB-like kind of a policy that looks at requiring very small volumes of these Leapfrog technologies. And so that could be an interesting route.
And there is also discussion about a price collar in the low carbon fuel standard, especially a cost containment, a price ceiling of some sort, and potentially a price floor. Those are under discussion currently.
Great. Maybe just a quick, there was a question that came in earlier related to what HFO stands for.
Oh, that's heavy fuel oil. It's what ships use, although they're going to probably be transitioning to more of a diesel type fuel, but that's what it means.
Okay. And that was on slide 4. But and the next question that came in was, are you aware of any producers implementing carbon capture for the distillation process? And kind of, again, where would this fit in the hierarchy of the routes?
I'm not aware of any. There's not anything with carbon capture and sequestration. I believe there are some that are out there that are doing carbon capture for, or they have a pretty pure CO2 stream and that are going into as a carbon dioxide market, because it's a product for carbonation and those things. And I'm fairly certain there are some ethanol plants that are doing that, but I don't have any on the listed out that I can give you an example.
Gotcha. I'll just read this one here. There's an uncertainty of ethanol blending constraints in making the transition to cellulosic feedstocks more challenging, or should say the uncertainty makes it more challenging. I wonder if this has implications for whether carbon intensity policies that have a volume component like the RFS compare to carbon intensity policies that do not, like the LCFS. In other words, the question is, does one favor Leapfrog versus Transitional versus Incremental, looking at the two different policy regimes that are in place?
I guess I need that reread or rephrased a little.
Yeah, does the, you kind of
it's
addressed
kind of like
it in
a
your...
blend wall question, and then it sort of turns into a volume versus carbon intensity question.
Yeah, so maybe it's kind of two different parts.
Yeah, right. I mean, I think the volume, the volumes, if you can implement them, they're a way to try to get volume. But if you've got significant barriers to do that, either you have to give the time to overcome that barrier, and you have to give the incentive signal that allows you to overcome that barrier.
One of the things that the carbon intensity version gives you, if there is a demand constraint on the ethanol side, and that becomes the binding price-setting constraint in the market, then that will ratchet up the LCFS credit prices, possibly to a point where the Leapfrog technologies would become more attractive to substitute in really low-carbon ethanol. There would be definitely some concern in my mind on the timing of how that all plays out and whether the policy is durable enough to survive that spike.
Right, that's sort of the issue with all those. I mean, that mechanism should really occur in either program. I think with the carbon intensity program, you have sort of more routes to get to your target, so you wouldn't expect it to happen, you wouldn't expect to hit that constraint quite as early. because there's more flexibility in how to comply.
Great. So we have a question here that relates to one of the specific slides. I wonder if you can go to slide 12. And I think this is the entrance into the market. So what was the what do we think is the attribution or the contributing factors to the spike between 2005 and 2010?
It's a good question. There are probably a number of factors, and we can all chime in on what we think. I mean, for one thing, oil prices were rising during that time. Concerns were very high. Let's say maybe it was a little bit now we're into a phase where we're discovering how hard this is, and that was, a time when people were really coming in to take advantage of all these new technologies and begin to do the scale up, and then the scale up is turning out to be quite challenging. There was also, I'll have to look at the slide about the breakout of the funding, but in terms of venture capital, it was a time when there was a lot of venture capital available that kind of started to dry up when we hit the Great Recession. So those are a couple of the parts of it.
And the renewable fuel standard definitely played a large role. Passed in 2007, and so but that is a little bit pre. So there was a build-up before that, though. So that may have had something to do with whether the policy got put in place.
So I have another question here that I'm going to expand a bit, and I'm going to try to pin you down a little on Nathan. It says, what are the costs of the 4 Leapfrog refineries in dollars per GGE? And maybe if you don't know specifically, you can comment on some of your work looking at sort of the transition between pioneer facilities and more mature sort of end plant or commercial facilities. And what might we expect in terms of the economics of these Leapfrog technologies?
Okay, so the only way I can think about it is to break it down into some components. The Leapfrog technologies, at least as they're being built now, are being built at smaller scales than you would like them to be built, based on optimization of the economics of the system, because they're constrained in the amount of capital they can raise. So that increases your dollar per gallon capital cost. And so that has an effect. So there's that part, and then there's the fact that they're unknown technologies, based on a study on pioneer plant facilities, it's kind of expected that the capital cost will be around twice what you would expect in the long run. And these facilities have been coming in better than that, but as we stated earlier, they're not operating at their capacity, so they're not done investing. So we don't know the final cost of them. And then the other factor is once you have a high per gallon capital cost, and that's on operating at full capacity. The question is how much do they operate? And so say Kior last year operated at best 50% capacity, and so that doubles your capital cost again. So these things add up and lead to somewhere pretty high.
And then in the future?
And in the future, you get rid of some of those problems, and they go down as you learn. You start operating at full capacity, get your yields up to your expectation, and things come down to. Eventually, you get down to where you expect to be, where you thought you would be when you built them.
We're thinking maybe getting close to or eventually below the production cost, sort of gate prices, refinery gate price of petroleum fuels. But the question is how long does it take to get there? And then going back to Nathan's comment about capacity, so this slide is showing that these capacities are, here it's between 8 and 20 million gallons a year. And Nathan, what would you say would be a target for these kind of facilities? I mean, for full scale, it's more like 50 to 100, right?
50 to 100, yeah.
So we're still looking at, something well below true commercial scale. And so it's going to take time for people to have the confidence to build such large plants and be able to run them at something close to full capacity. But once they get there, and then we get the optimization and learning that we're We're hoping, we always talk about the nth plant. We don't know quite how many plants it takes to get to the nth plant, but those are all parts of it to get down to competitive production costs.
Great. So I think we have time really for one more question here. Maybe two I'll throw out to the group. One has to do with very specifically what the impact of co-products might mean for Incremental versus Leapfrog. And then the second question is a little bit different. It has to do with we're having another webinar here later today on the carbon balance for biofuels, and what do we think that might imply for the policy regimes that we're talking about.
So this is Geoff. I'll take a stab at the co-products question. I think what's being asked is, well, I'll just say, in general, if you make better co-products, depending on where in your life cycle assessment you're drawing your system boundaries, a lot of co-products have the potential to drive down your carbon intensity. With corn oil is an interesting example that the person asked about. Right now about 80% of corn ethanol plants in the U.S. are now producing corn oil in addition to the distiller's grain. And so this is a very recent development in the last maybe 8 years. And, again, depending on where you draw your system boundaries, that corn oil, can be used for replacing, other oil crops, and so you might be reducing your carbon intensity.
Yeah, so for the second question, it sort of raises this big issue that we've been alluding to throughout. With the current rating system, it sort of touches on this mostly through the indirect land use change, trying to actually capture larger effects. These are not small scale-ups that are being talked about, small productions, and so you would expect them to have larger ripple effects through the system, substituting fuels and so forth. And so for policy analysis and policy evaluation, it really calls for a more complex, comprehensive look. And then, once you have that idea, building your incentives in the policy, which is currently in this carbon rating system, building the incentives to the producers that reflect the overall, the overall carbon effects. And right now, those two things are put together, and it's causing there's some tension, and there's a need for the systematic analysis and to draw that line back to the incentive system. So I think the land part will only become more important and raises the flag for how important it is to look at the energy transport energy system in conjunction with how emissions are occurring in the rest of the economy.
And that takes I don't know if you were specifically responding to the question about John's talk. Okay, so you were.
Yeah.
But so that is a nice segue that this afternoon there will be a presentation here at ITS from John DeChico that does look at the whole elephant maybe, or big parts of the elephant. And, it all matters. We've got to figure out how to make the incremental improvements. We're already, we've got over 200 corn ethanol plants in this country. Making them better is a good thing, but we also have to step back and look at how the whole system works. So, see that talk as well.
Great, thanks a lot. I want to thank the panel today, and I want to thank all of you who've taken time out of your day to dial in. You will be receiving a very short survey just to give your feedback on how you found this webinar, any suggestions for future improvements. Also want to encourage you, if you're not already signed up for a distribution list, this is the first of a series. So you will be receiving invitations for future webinars that will be in partnership with the Sustainable Transportation Energy Pathways Program, and we hope you dial in for those as well. So thanks again, and have a great Friday, and have a great weekend. Thanks.